Hello everyone, welcome to this presentation entitled Piecewise BJT model for LTspice. This is the outline of this presentation. We will see the introduction, then we will show how to model the NPN BJT using a piecewise linear model. We will test our model doing several simulations. Then we will see how to implement this model in LTspice. And finally, we will see how to implement the piecewise linear model for a PNP BJT transistor. What we want to implement now is the piecewise linear model of a BJT transistor. For example, here we have the NPN transistor. We have these characteristics here to model the behavior of the transistor. And we have the input characteristic, which represents the base current versus the voltage between the base and the emitter. So we have this relationship. We are modeling in such a way that if the voltage is lower than the threshold voltage, the current we can consider that is almost negligible. And then if the voltage VBE is greater than the threshold voltage, we have a linear relationship with a given slope that we can quantify as a 1 over resistance RBE, which is the series resistance of the base to emitter junction. And from the point of view of the output, we have the output characteristics, which give the current through the collector versus the voltage between the collector and the emitter. So these are typical characteristics using a piecewise model. And then we have the three operating areas. We have the active region in which the transistor behaves as a current source with a small slope, as we can see here, that we can model also with a given resistance. So the slope here, we can consider that this slope is given by 1 over the resistance between the collector and the emitter. Then we have the saturation region, which is this line here, in which we consider that the current versus the voltage is linear. And also the slope of this saturation region can be given by 1 over a given resistance that we are going to call R sat. And finally, we have the cutoff region, so it's represented here in black. So when the current through the base is 0, then we have a behavior that we can model also as a resistance with this slope here, which is also given by 1 over RCE. So these are the equivalent circuits in the different operating regions. For the active region, we have at the input between the base and the emitter the equivalent of a junction. So we have the series resistance of the base to emitter junction and the threshold voltage. So we will be operating in this part here, and therefore the condition is that the current through the base has to be greater than 0. And for the output characteristics of the transistor, we can use this model in active region to model this part here corresponding to the behavior nearly as a current source. So we are using a current source with the value beta times IB, the current through the base, where beta is the DC current gain of the transistor. And in order to model the slope of the characteristics in active region, we add this series resistance here, RCE, and this voltage source, V sat prime, in parallel with the current source. So with this, we will be operating in this part here corresponding to the active region. Note that the value of V sat prime is different for each curve. So for example, if we select a base current corresponding to this line, the active region goes from this point to the right. If we select this other value here for the current through the base, the active region goes from this point to the right, and so on. So the condition to be in active region is that the voltage between the collector and the emitter in this equivalent circuit. The voltage between this point and this point has to be greater than Vsat prime. In the saturation region, we have at the input the same equivalent as in the case of the active region, because the junction between the base and the emitter is in forward state. So we have also positive current through the base, and on the output characteristics we will be operating in this part here on this line, depending on the level of the current through the base. So for example, for the current through the base corresponding to these characteristics, the saturation region goes from this point here downwards. So this is also important for each curve. For example, for this other curve, this is the active region and the saturation region go from this point downwards. So the condition to be in saturation region and to be able to use this equivalent circuit is to have the collector to emitter voltage between the saturation voltage Vsat and the saturation voltage for this corresponding curve Vsat prime. And then we can model the output using this series resistance and this voltage source. And finally, in the cutoff region is when we have no current circulating through the base. So in this case we are operating in this part here, so the voltage between the base and the emitter is lower than the threshold voltage, so the current is negligible. So we can represent the transistor between the base and the emitter as an open circuit, and the condition is that the voltage between the base and the emitter has to be lower than the threshold voltage. And for the output of the transistor, we can model this part here, the cutoff region, by using a series resistance and the voltage source Vsat, similarly as in saturation region, but in this case the series resistance has the value RCE, which is the same that we use in the active region. And the condition to be in this region, in cutoff region, is that the voltage between the collector and the emitter has to be greater than Vsat. So we are from this point to the right. We have another part corresponding to cutoff region which is below Vsat in this model, and in this part here the current through the collector is considered negligible, so it will be implemented as zero current. So the point now is to develop a model for our BJT transistor for LTspice that is going to incorporate these three equivalent circuits in a single model, and then we can use this model to simulate the transistor in our circuits. So the idea is that usually when we teach this type of circuits using BJT transistors, we model the transistors with these simple models, piecewise linear models, and then using the built-in models that we have for the BJT transistor in LTspice, it's not possible to get the same values that we get when studying the circuits with a piecewise linear model. So I think that this is very interesting also for the students to have this type of models, so they can study the circuits and then do the simulation to check if the analysis is correct. So here we have the LTspice model that we have developed. The idea is that between the base and the emitter, we use the typical piecewise model of a diode. We employed an ideal diode here, D1, the series resistance, RBE, and the series voltage source, VTH. So with this, between the base and the emitter, we are going to have this characteristic. And from the point of view of the output, we use the current source with this value, beta, the DC gain of the transistor, times the current through the base, so it's the current through this diode here, D1. And then we use these branches here to model the three operating regions that we have for the transistor. With this voltage source, we implement the value V sat prime, because the value V sat prime, as we are showing here, can be calculated with the value V sat, which is a parameter of our transistor, plus the value beta times the current through the base times the resistance R sat. So the value beta times IB0 is the value of the collector current at this point. If we multiply this by R sat, we have the difference between V sat and V sat prime. So the idea is that if the voltage, the collector to emitter voltage, is greater than this, then this branch is going to conduct, and we have the effect of the parallel resistance RCE. So we will have a behavior like this if we calculate the equivalent circuit of the current source in parallel with the resistance, with the series voltage source. We are going to have this behavior that we want for the active region. And then if the voltage between the collector and the emitter is lower than V sat prime, then this diode here is going to conduct. This other is going to be open, so we have the current source in parallel with the voltage source and the series resistance R sat, and then we will have this behavior here for the saturation region. And finally, we are adding here this other ideal diode. So we are assuring that the collector current of the transistor is going to be always positive. At the end, we are interested only in modeling the behavior of the transistor in the first quadrant. So we are using this diode here to avoid that at some point this voltage source here can generate at the end negative current out of the collector pin. So finally, this is our model, and these are the parameters of our model. We have in total 6 parameters. We have for the input the base to emitter resistance, the base to emitter threshold voltage, and for the output we have the DC current gain, beta. We have the saturation voltage, the saturation region resistance, and the active region resistance. So now we are going to do a simulation in LTspice to obtain the characteristics of our transistor to see that the model is operating well. What we are doing is to use a voltage source here and a series resistance to inject a given current through the base, and then at the output using a sinusoidal voltage in series with a resistance. We are going to generate different points corresponding to the current through the collector and the voltage between the collector and the emitter. And we are doing this for several values of the voltage VDC, so it corresponds to several values of the current through the base. These are the parameters that we have employed, and then we are going to do a transient simulation. And what we want to do is to represent the output characteristics of our transistor, because the input characteristic, it's clear and that we are going to have the behavior that we want, because it's very simple circuit. So we are not going to do that. We want to represent the output characteristics which are given by the current through the collector versus the voltage between the collector and the emitter. So we can measure the current through the collector by measuring the current here through resistance R2. And then we have here the characteristics in time. So we want to represent this as a function of the voltage, as a function of the collector voltage. So we change the x-axis and use V of C here, and here we can see the characteristics corresponding to our transistor. So these are as expected. We have the saturation region, we have the active region, and this corresponds to the cutoff region. But let's play a little bit with our model. Maybe we can do some changes. For example, if we want a more ideal transistor, we can use a higher value here. So let's first run the simulation to see everything together. And now if we change here the value, for example, if we increase here the value to 100k and run the simulation again, we can see that now the slope of the curves in the active region and in the cutoff region is almost negligible. We can do other things. For example, if we want to have more ideal behavior in the saturation region, we can decrease the resistance RSAT. So maybe here, if we use only 1 ohm and run the simulation again, so we can see that the behavior is now more ideal, but still we have 0.5 volts for the saturation region. We can do even our transistor more ideal, so we can maybe select here VSAT smaller, maybe 1 millivolt. So we can run the simulation again and we can see that now we have an almost ideal transistor. This is an example of application of this model. For example, if we want to analyze a circuit like this and we are modeling our BJT transistor with these piecewise models, as shown here, this is for the base to emitter junction and this is for the collector to emitter behavior. So we can see that we have a piecewise model and we analyze this circuit as shown here by calculating the parameters of our transistor. We substitute the base to emitter junction by the resistance and the voltage source, and between the collector and the emitter by the current source. In this case we don't have resistance in parallel with the current source, and we do all the analysis and so on. So in this case, we can use our model, our BJT model, to do the simulation and verify that everything is correct, and we will obtain the same values for the collector voltage, for the base to emitter voltage, for the current through the base, and so on, exactly as we have done in our analysis considering the piecewise model. This is not possible using the models that we have in LTspice, the built-in models in LTspice, because they are not exactly what we want when we are doing our analysis, as shown here. So this is the implementation in LTspice of our model. This is the symbol that we are going to use, and these are the 6 parameters that we have for our model. This is the schematic of the model. From this schematic we can obtain the description for the library, and with this we have everything to implement our new component. If you are not familiar with this, please take a look at these videos, LTspice number 3, how to create new components, and LTspice number 4, also how to create new components from schematics. We can also do a version for the PNP BJT transistor, so we can use this symbol here. These are the parameters, and here we have the equivalent circuits. So in principle we only have to reverse all the components. So between the base and the emitter we have the ideal diode in this direction, the series resistance, the voltage source also in this direction. The current source goes now from the emitter to the collector, and the branches also go in the other direction. So it's very easy to obtain this model, and then here we have the description for the library, and with this we have everything to implement the piecewise model for the PNP transistor. Here we have a quick test of the model corresponding to the PNP transistor. Note that the components are going to be available in the control library. So they are here, PWMPN and PWPMP. So now we can run this simulation and see the results. Now we want to represent also the characteristics. So now we are going to measure the current out of the collector using the current through resistance R2. And we are going to represent this as a function of the collector to emitter voltage. But now, because this voltage is negative, we are going to use here, instead of VC, we are going to use minus V of C to see everything better. And then here we can see that the characteristics are as in the case of the NPN transistor. So the model of our PNP transistor is also operating well. Finally, if you want to save time, you can go to my website. This is the link. And then in the part corresponding to resources, you can download the last version of the control library. And there you will find these models of the BJT transistor. Well, with this we get to the end of this presentation today. I hope that you find these models useful. Please let me know your comments and your experience using these models. Thank you very much for watching this video, and I hope to see you in the next one. Goodbye now.